Okay.
And I only did the
Let's
first
begin.
one. Yeah, you have unlimited tries, but it doesn't help you. It's really depressing.
So, I'm pretty sure the last lecture, somehow the end got cut off a little bit. So I'll start by repeating myself just a little bit, which is, I don't know, probably a good idea anyway, because you can get to review something. So, or maybe I'll go back even a little bit further. So, we have been looking at several kinds of ways interest is applied. Two main categories, the one-time payment categories, where we have simple interest, we have compounded interest, and we have compounded continuously interest, or continuously compounded. I mean, there's no standard way to say this, I don't think. Right? So whenever we're dealing with one-time payments of, say, P, we can assess the future value of the amount invested by that, if it's simple interest, where R is the APR, T is the time in years. In the compound interest case, this is P times 1 plus R over N to the N times T. So this is when interest is only assessed on the original amount invested. This is when interest is assessed on top of interest as well as the original amount invested. And this is if you do that an infinite amount of times theoretically in some time interval, and that leaves the PERT formula, kind of like the shampoo. So that was whenever you're reading a problem and there's some sort of idea like a one-time payment, like something's happening one time, and then you're just checking one point in the future for some answer. This is kind of where your mind should be going. It's one of these formulas somehow, depending on what is stated or how the interest is being applied. Now, there were a couple ways in which we looked at multiple payments. And by our assumption, to make things a little bit easier, we're looking at multiple regular payments. Right, so in general, if you have some sort of situation where you keep paying, either you keep investing a certain amount, or you keep paying out a certain amount, either receiving or paying out to someone else. We had two situations there. These guys were called annuities, and there was, I believe we started with the future value of annuities. And the main formula there was called the sinking fund formula. And that basically said that the future value was equal to the payment value times 1 plus R over N to the NT minus 1 over R over N. And we had the present value of the new, usually referred to as the amortization formula, because it's useful when you're trying to figure out when you want to put a debt to rest, and amortization needs to kill, in saying it in a very nice way. And you can talk about that in terms of payments as well. But this is 1 minus 1 plus R over N to the minus NT to the R over N. And I believe those were all the forms I gave you. There was something in the homework about time-weighted interest, and I gave you guys a link to look that up. I'm not going to ask you about that in class, but it's just something you can know for the homework, or you should know in general. And I also mentioned, so these will be clear because if I give you a problem that has to do with one of these, the phrase itself is going to be present in the problem. Like it's going to say, it's compounded this many times per year, or it's compounded continuously, or we're applying simple interest. The actual phrase is going to show up in the problem. In problems where these guys show up, you might not see the actual phrase sinking fund, or the future value of annuity, or amortization, or anything like that. But you'll notice that they use very similar variables, and so how do you know when to use one versus the other? And it kind of all depends on what the end game is. So as I mentioned last time, we're looking at, let me just put it over here, have more space. If we were looking at sinking fund versus the amortization, how do you know when which formula applies? Well, it depends on, like I said, the end game. So this one comes down to you're making payments now. To build up to a lump sum in the future. So you tend to want to think of this when you're saving up or investing for some future goal. Right, so based on the situation, so if there's a problem like, oh, a mom wants to start a college fund for her kid and she knows she wants to be able to send him to college when he's 18 and she assumes that this will be how much she's sending him, this is the formula that you're going to use, right? Amortization would come in when you put a lump sum now, right, which is the present value that you're putting down now, in order to have payments in the future. Right? So you're looking for payouts in the future. Now, if the payouts in the future is going to someone other than you, that is you paying back a loan or a debt. So this, you want to think of paying down debt is also something. So if you have a problem where it's like, oh, someone's taking out a car loan or someone wants to get a mortgage to buy a house or something similar to that effect, amortization is probably the form that you'd want to use on that problem, right, as opposed to this one. And so we want lump sum needed to get or give multiple regular payments in the future. So that's basically the idea when you use one versus the other. And like I said, the word problems that appear for these two, they aren't going to be as clear cut. You kind of have to read and understand the situation, what's actually going on, and then you choose what formula you're using based on that idea. And as I also mentioned, this was to end the class, which I think around this point the video got cut off for some reason. The above can be mixed and matched. So, I probably won't ask you a problem on like a test where you have to mix both of these, but like on your project, the group project that you'll be getting, you'll be mixing both of these kinds of ways to look at money. So, and the example that I mentioned was kind of just a timeline when you're looking at someone's life. Right, where you kind of look at a beginning, a middle, and an end, and this was like you at 20. This is you at 60, and something like this is you at 80, which is Ed, right? So you expect it to die at 80, right? For some reason, you just say, I just want to have enough money at 60. So I could retire, right? Like here's where you wanted to retire. And I want to be able to live off whatever money I saved up until that point. I want to live on that for the next 20 years where death is expected to occur. At which point if I live past 80, I don't know, you have to rob a bank, get a job. I don't know what you're gonna do if you live past 80. But that's if you're planning things out this way. Over here is where amortization becomes important. Because the idea is you need some lump sum here that's going to give you regular payments coming out. Whereas at this point, when you're 20 and you just got your first job, what you're doing here is you're saving up, right? So with every paycheck, you're taking a little bit and you're putting it into an account. Hopefully you're investing it so it appreciates and you're not hiding it under your mattress where your money actually gets devalued because of inflation, right? So over here is where the sinking fund would apply, right? So if you're looking at your entire life, the first half of it, or your working part, the sinking fund is going to be very important. That's when you're saving up, that's when you're building your wealth. And the last leg of your life, when you kind of just want to chill and do your own thing, and hopefully that comes much earlier than 60, but I'm just talking about a typical average example here, the amortization formula would become a lot more important. Okay. So you make regular payments here, so you can save up to some lump sum here, that's going to give you some payouts for the other side. So you could, if you're planning out something like this, you would have to use both, but you need to know when to use which. And yeah, that was basically all I wanted to do with the financial math, other than what's in your homework and your project, which you guys will might have to supplement what I'm telling you with your own research a little bit, which is intentional. But yeah, that's kind of where we are. That's kind of where we left off, which was forever ago. Any questions on, like, in general about what we did with financial math? Kind of all realize when we want to do which thing. So now we are going to move on. We are going to do something very different. We're going to learn about a new way of looking at things for some people, not everyone. Some of you would have noticed this. But we're going to move on to talking about matrices and matrix algebra. I don't even remember what chapter this is in your textbook, probably chapter 4 or 5 or something. And matrix algebra. So matrices, by the way, this is the plural of matrix. Not where Keanu Reeves is, this is something else entirely. It's a mathematical object. We're going to look at these objects, how they behave mathematically, and we're going to use them for all sorts of applications, including Markov chains towards the end of the semester. But prior to that, we're going to be using them to solve systems of equations. And because of experience, at this point I just want to lead with something and nip it in the bud. A lot of you know how to deal with systems of equations already from high school without using the matrices, and when I show you the matrices, at first, to some of you, it's going to feel weird, and you're like, do I have to use matrices? Can I do it the old way? Okay, you need to learn this, you need to learn it well, okay, for several reasons. So, no complaining about, I don't want to use matrices, it's important that you learn it this way that I'm trying to tell you, and you actually get good at applying this way. And like I said, for several reasons. One, you're all my kids, I want the best for you, I want your futures to be as bright as they can be. Now, one way in which it's bright as it can be is for you to foster the habit of being open to new ideas and new experiences, okay? So don't be afraid to try something new. Don't continue to do something simply because it's always been done that way. It limits you, right? So in that sense, learn something new. Even though if you know how to do it another way, it's good for you to branch out and say, hey, this way might be more interesting, or I might be able to use this way when I can't use the other way. Secondly, it makes your future brighter because when it comes down to, a lot of you want to go into finance and that sort of thing, when it comes down to really the technical application of business, the technical application of finance, these guys are indispensable, right? So if you're thinking of you're being a quant, you're going to be one of those guys who's on a board at Goldman Sachs telling people what to do, you're going to have to be very familiar with matrices. And not where the kinds that I'm showing you, we're going to talk about like 2x2s and 3x3s, maybe a 4x4 and a 5x5 here and there. You're going to be dealing with matrices that are literally thousands of rows and columns long, maybe millions even sometimes. And you're going to need to know how to deal with these objects, how to write programs regarding these objects. It's going to be very important that you know how to deal with matrices. Because the way technology is going and everything's being done on a computer, and now there's AI and all sorts of stuff, matrices applies to all of that. So if you're going to want to be one of the business tech savvy people of the future, you're going to need multivariable calculus. You're going to need linear algebra, which involves matrices. You're going to need probability. You're going to need statistics. Do not fear these things. So some of you might be, man, I'm a business student, I'm all about networking, man, I'm this guy, right? So the thing is, if all you can do is this guy, you're the first person that's gonna get laid off. That's important, don't get me wrong, but if that's all you can do, there's gonna be someone else who can be this guy and at the same time can be this guy and be like, yeah, you need 2% over here, you need 5% over there, fire these people over here, hire those people over there, ship from this point to that point, that's gonna be the shortest route, right? To figure that stuff out, like on a numbers level, at some point you're going to be using this. So it's very important that you learn these things and not just, okay? So at the beginning, especially if you don't have a lot of experience, like I said, it's gonna feel a little weird. Why do I have to do it this way? Just take your time, it'll take some time to get used to, and you will learn. And there are times when talking about this is gonna be very intuitive, there are times when it's not gonna be very intuitive. I will point these things out to you. But yeah, let's actually just jump into it with that said. So, no complaining about it. We're doing matrices, okay? Okay, so definition. What is a matrix? Now, if you're a math major, this is not a good enough definition, but for pretty much everyone else, this is fine. A matrix is a rectangular array of numbers. That's it, that's what a matrix is. You write a matrix in a rectangle, you write an array of numbers in a rectangle. So the notation would be something like, okay, 1, 2, 3, 4. That's like you write numbers in the form of a rectangle. It doesn't have to be a square. You can have 1, 2, 3, 4, 5, 6. That's another kind of rectangular array of numbers. You can have a 1 guy. It's a very small rectangular array of numbers. These notations are very common. You can also use like the square brackets. They're completely interchangeable. So I could write all of these with square brackets. I tend to write it this way because it's easier. You know, I can just do boom, boom instead of it takes too long. So I'm just gonna do it this way. So one important thing is, and will we be talking about this? Maybe. Not like a straight thing, right? If you write a straight line, it's not a matrix, it's something else. This is something else called the determinant. Now I probably won't be talking about that, but this is the determinant of the matrix. 1, 2, 3. So you can use parentheses or you can use brackets, that's fine. Do not use straight bars, it means something completely different. Okay. But that's all a matrix is. Now let's talk about some definitions. A lot of this, me introducing this, is going to be a lot of definitions. But we'll try to get to the math as quickly as possible and some more interesting things. So, the numbers in the matrix. We call these the components or elements of the matrix. Now, here's another definition. Horizontal sequence of numbers. We call these rows of the matrix. Vertical sequence of numbers. We call these columns. And this guy here, it's numbered from top to bottom, starting at 1, and this one numbered from left to right. Starts at 1. So if I have the matrix 1, 2, 3, 4, 5, 6, then this here, this is row 1. This here is row 2. Right? Rows are a horizontal sequence of numbers. You start numbering them top to bottom. This here is column 1. This here is column 2. This here is column 3. So vertical sequences of numbers are called columns. They are numbered from left to right. Other definitions. A matrix with m rows and n columns is called an m by n matrix. So you state the number of rows first, the number of columns second. So if I'm at 1, 2, 3, 4, this is a 2 by 2 matrix. If I look at 1, 2, 3, 4, 5, 6, this is a 2 by 3 matrix, and so on and so forth. And like I said, in applications, these guys can be thousands of rows, millions of rows. And I'll actually mention some particular examples where matrices would get that big much later on, probably. But those are how we talk about. This is called, and this refers to the size or dimensions of the matrix. So if I say, what's the size of this matrix? It's a 2 by 2. What's the size of this one? It's a 2 by 3. 2 rows, 3 columns. State the rows first before the columns. We can name matrices. So I could say, let A be the matrix 1, 2, 3, 4, and then from that point on, wherever I use the uppercase letter A, you know, oh, let's talk about the matrix 1, 2, 3, 4. I can refer to it by a name, and it's very common. It's usually an uppercase letter. Of course, it usually means not always, but chances are, if you see two things together, like if you see little a followed by a big A, this would be thought of as a matrix, while that is thought of as a number. Right? That's very common. What else do I want to tell you? The element. Oh, another word for element is entry. So you can have entry, elements, components, they're all the same thing. In the ith row, jth column is called the ijth entry, and denoted using a corresponding lowercase letter with subscripts. So for example, I'd use lowercase a with little ij here. So usually if your I and j are 1 digit long, you put it like that, it's understood. You might put a comma. If you're like hundreds of digits long, you might separate it with a comma. maybe I'll do an example there. So if my matrix A is actually 1, 2, 3, 4, 5, 6, I can talk about the elements A11, A12, A13, A21, A22, A23, and I can refer to these numbers of the matrix over here, and I can say this is the element that's in the first row and first column. So this is the first row, first column, that's the guy. So that's going to be the 1. And then the first row, second column. First row, second column, that's the 2. First row, third column, that's the 3. Second row, first column, what's that? That's the 4. And then this would be the 5. And then that would be the 6, but that we would call it. And we may call A to be, they might use that. So if you put these little things with parentheses around them, it's referring to a matrix, and for emphasis we might denote the size 2 by 3. So they'll use that a lot when they're proving matrices. It's a nicer way to actually explain what's going on in the proof. So what are matrices? We can name them, the elements, the rows, columns. Am I forgetting any definitions before we move on? Let's just make sure. From the bottom. Okay, so I told you about entries, dimensions, I told you about that stuff just now, Okay, square matrices and equality of matrices, and then we start getting into addition. Okay, cool. So, if m equals n, A is called a square matrix. These guys are going to be important because there are certain things that they always have to, that can only be done with square matrices. It was funny, I have a friend, he was in academia for a while, but then he went into finance, and there was a point where he was hired by this firm to solve some kind of problem. It involved matrices, but no one there could do it because no one took matrices seriously. Anyway, so they hired him as an outside consultant and say, "Oh, we're trying to get this done, but blah blah blah. It won't work, and we want you to figure out a way to make it work." He goes in on the job, and day one he's like, "Yeah, what you're trying to do is impossible," and then that was it. And got paid thousands of dollars just for them to know that it's impossible, and they're not putting in all sorts of man hours. And it was very simple. He envisioned the problem as a matrix and realized the thing that they want to get done, the matrix has to be square in order for it to work. And then he realized, oh, it wouldn't be a square matrix, so it's actually mathematically impossible for you to get this thing done. So square matrices are important. There are certain things like finding inverses and things of that sort that you can only do with square matrices, and I'll talk about those. We'll talk about those when we get there. Quality of matrices. Two matrices are equal. So let's call the matrices A and B. A and B are equal. And we write A equals B if they are the same size and corresponding entries are the same. and thus it begins. So at this point I just wrote that down, and you might have the thought, well, isn't that obvious? Okay. Having that thought when it comes to matrices is a dangerous thought. There are some things that would seemingly be obvious, and there are some things that are very not obvious. So whenever something's obvious, I'd still write it down so you can know, okay, you can consider this obvious. There are other times when something is not obvious, and I'm going to tell you, hey, you might feel like doing this, but it's not going to work when you're doing matrices. So if I say something like, oh, this matrix 1, 2, 3, 4 is equal to some other matrix over here, 1, x, 2 plus y, and 4, then you can assume that the corresponding entries are the same. So this must match up to that, this must match up to that, this must match up to that, this must match up to that. And of course you can conclude from this directly that x equals 2, and you can conclude that 2 plus y must be equal to 3, so your y must be equal to 1, right? So you can make these conclusions here. So the only way I can even make the same end in the first place, this is a 2 by 2, it has to be equal to another 2 by 2, and the entries in the 1, 1 position, the 1, 2 position, the 2, 1 position, and the 2, 2 position have to be exactly the same. And we call the matrices equal when that happens. And I understand that this seems like a stupidly obvious definition, but don't think of anything in matrices as being obvious. Because I know we think of them as rectangular array of numbers, but the real mathematical way to think of them is as functions, and functions can behave kind of sketchy sometimes. They don't just behave like numbers on the number line. Let's talk now about addition and subtraction of matrices. Let's do some math with these guys. Again, the next two operations, they're going to seem very obviously defined. I'll write them down anyway. We can add or subtract two matrices. The same size. So in order to add or subtract the matrix, they have to be exactly the same size. By, you might guess, it might seem obvious, but again, perish the thought, by adding or subtracting their corresponding components. Yeah, that's it, that's how you add two matrices. So, if I say A is the matrix A, little I, little j, let's say this is an n by n, and B is the matrix little b, I, j, this is also an n by n, then it means that I can add A and B, and that matrix is going to look like Aij plus Bij in each component, and it will also be the size n by n. Do I give examples now or later? I will give examples later. So far we're doing definitions, so there's nothing new. There are no real questions to ask at this point, it's just a matter of, this is how it is, this is what we call everything, this is how they fit together. So it's just something to know, not really to understand, unless you're a math major, which you wouldn't be here if you were. There is something called scalar multiplication for matrices. Scalar is a fancy word for constant. And so let K be a scalar. Let A equals Aij be a matrix. define KA to be the matrix, this guy, right? It's just the matrix A where each component in A is multiplied by K. And this is called a scalar multiple. So I'm multiplying a scalar by a matrix. Okay, those are all the definitions. Let's actually do something because it's getting boring. Even I'm getting bored writing down all these definitions. So here, I keep thinking that's someone's hand being raised. It's the camera. So here's an example. So here are some matrices A, which I would take to be 1, 2, 3, 4. B, which I would take to be 2, 0, 1, minus 3, 1, 4. C is the matrix 7, 1, minus 1, 0, 1, 2. D is the matrix 0, minus 1, 2, 2. I would like you to compute all of these. A plus D, B, A plus B, C, D minus A, D, B minus C, E, 2A, F, 2D minus 3A. G, 1/2 D, H. The X plus D equals A. Find X. Let's actually do these together. So, A plus D. So this is like I'm saying 1, 2, 3, 4 plus 0 minus 1, 2, 2 equals, what is that equal to? Go.
1, 1, 5, 6.
So that's the answer. Note that what he did was 1 plus 0, 2 plus a minus 1, 3 plus a 2, 4 plus a 2. You add the corresponding entries. Now, you don't necessarily need to write this down, but you should know how to get from here to here. Just add corresponding entries. Okay, cool. B. What is A plus B? Huh? So A here, what size is this? This is a 2 by 2. Let me write these down. So A is a 2 by 2, B is a 2 by 3. It's also a 2 by 3, and this is a 2 by 2. Now, because this is a 2 by 2, that is a 2 by 3, they cannot be added together. So this is undefined. C. D minus A. Well, these are the same size, so they can be subtracted. This is 0, minus 1, 2, 2, minus 1, 2, 4. And very similar to subtraction, you are going to subtract the corresponding components. So you're going to take the first one minus the second one, 0 minus 1, minus 1 minus 2, 2 minus 3, 2 minus 4. And so the answer to that would be minus 1, minus 3, minus 1, and minus 2. One thing that can be frustrating with matrices is that we're never going to be doing anything complicated with them. It's always going to be like arithmetic, like us adding and multiplying stuff. But it's going to be easy to make a mistake at the same time because you're doing a bunch of additions and subtractions at the same time. It's easy to just slip up. So just be careful with that. Can we do B minus C? Yes, they're both 2 by 3s, so I know that's possible. I mean, at this point, I think we sort of get the idea. So I'm just going to do this. So that's going to be 2 plus 7, 0 plus 1, for subtracting. 2 minus 7, because the B is that. Okay, 0 minus 1, 1 minus a minus 1, minus 3 minus 0, 1 minus 1, 4 minus 2. Minus 5, minus 1, 2, minus 3, 0, and 2. Or I just did D. E. 2A. So this one is slightly different. So it's 2 times the A, which here is 1, 2, 3, 4. This is a scalar multiplication. So all we do is we take the scalar, we multiply each individual number. So again, you don't have to write this, but you should understand what's happening here. So this is the 2 times the 1, the 2 times the 2, 2 times the 3, 2 times the 4, which gives you 2, 4, 6, 8. And F. D minus 3a. So it's the same idea. You probably just write them out a little bit first. So we have 2 times the D minus 3 times the A. So this is going to be 2 minus 2, 4, 4, minus 3, 6, 9, 12. And so this is going to be 2 minus 3. Is a minus 1, minus 2 minus 6 is a minus 8, 4 minus 9 is a minus 5, 4 minus 12 is a minus 8.
2 times 0 would be 0.
0. See what I'm talking about?
So that would be 0.
So this will be negative 3. Yeah, eventually you just underestimate it. You're like, whatever, this is stupid. Then, oh my god! You get something that's... Yeah, do that at Goldman Sachs, you just lost $5 billion. They just sell you in your fund. Okay. Yes, where are G? Yes, 1/2 D. Again, this is like 7 minus half. 1. I think we're going to get matching it. Okay, so X plus D equals A. How do you solve X?
A minus D.
Yeah, you can just like do A minus D. Now, I there's something I want you to appreciate here. So yeah, I can do A minus D, 1, 2, 3, 4, minus 0, minus 1, 2, 2. And so this is going to be 1 minus 0, 2 plus 1, 3 minus 2, 4 minus 2. Okay, so that's going to be the idea. But I do want you to appreciate what happened here. And there's going to be a reason why, even though it's like, why are you torturing us, Jhevon? Come on, it's obvious. Okay. So here's what actually happens. So you had x plus 0, minus 1, 2, 2 equals 1, 2, 3, 4. And what you decided to do was subtract d from both sides. Now this can actually make sense, because what happens here is if you follow the rules of addition, you get 0, 0, 0, 0. While if you just add 0 to every component of x, it's not going to make a difference. So this part here is just x. And over here you end up with the a minus d. Okay. So you have to be careful of your little arithmetic. So again, yeah, doesn't seem so bad. Are we cool with this? Some of you are like, what was that speed for? This isn't so bad. This is easy. This is easier than the financial math stuff. Just give it time. Hold on. I'm kind of just assuming that there are people in the class who have no idea what a matrix is, and so I'm really starting slow and building it up. Some of you, this might be obvious, and I'm sorry for making you bored, but here's a fun one, matrix multiplication. Okay. Who here has seen matrices before? Oh, pretty much everyone. Okay, cool. Who's never seen matrices before? Like, you've never done anything like this? Oh my god. Now it's gonna seem like I'm picking on, or maybe, I don't know if even the people who have dealt with them before, maybe you don't even remember how to do this. So based on, how you multiply matrices and how you add them, how would you guess that you would multiply two matrices? Like if I gave you 1, 2, 3, 4, and I multiplied it by 0, minus 1, 2, 2. What do you think the answer would be? Yeah.
Do like each corresponding spot to that.
Yeah. So you think it's 1 times 0,
Yeah.
and then 2 times minus 1,
Yeah.
3 times 2, and then 4 times 2. Does everyone agree? Yeah. No. Okay. So here, this is what I'm talking about. There's some things that are going to seem so obvious. Oh, yeah. I mean, adding them is just adding corresponding components. Why wouldn't multiplying them be multiplying each component? Okay, so, well, we'll see. To someone who remembers matrix multiplication, tell me how to compute this. Yeah.
Isn't it like 1 times 0 plus 2 times 0 is like the first term, and then
No.
I don't know.
Yeah?
1 plus 0, 1 plus 1 times negative 1.
Plus 1 times negative 1? No. Oh, so you guys don't remember. Oh, maybe it's a good thing I'm starting from scratch. You guys remember? Yeah.
Is it 1 plus 0 times 1 plus, oh no, plus 1 times 2?
No.
Okay. I get both.
2 times 2. 1 times minus 1 plus 2 times 2. And this would be 3 times 0 plus 4 times 2. And this would be 3 times minus 1 plus 4 times 2. Are you confused?
No.
Yeah, like why would this be the way to do it? But that's actually the way to do it. Now let's try to figure out what the heck happened here. I'm not sure I'll talk about what this means. Maybe next time. I don't know. But let me remind you how to multiply matrices, since apparently a lot of us don't remember. So the first is you have to recall there's something called a dot product. Between a row matrix and column matrix. Now on this level, it does work in the way you'd expect. No, even now it's still kind of weird. But it works similarly in terms of corresponding things. So let's say I have a matrix that just consists of one row. Let's say it has elements A1, A2, and A3 in it. I can call dot product that. This is called a dot product. With a column matrix, let's say a matrix that consists of one column, B1, B2, B3, and the result of that is going to be a 1 by 1 matrix that has the following formula. I'm going to take these guys multiplied together and add them together. So I'm going to take A1 times the B1 plus A2 times the B2 plus A3 times the B3. Now this, when you add these all together, it's going to be one number. So these two things, when we multiply them, or we call it dot product them, it all collapses into one number. Okay. So there's that idea. Okay. With that idea, I can now define matrix multiplication. So maybe I should give it a particular example. I don't know. So say 1, 2, minus 1 dot product with 0, minus 3, 2. That's going to give you 1 times 0 plus 2 times minus 3 plus minus 1 times 2. So that's going to be 0, minus 6, minus 2. This all collapses into minus 8, that one number. This is called a dot product. That's how you dot product these two matrices. Now let's define matrix multiplication. Now this definition is going to be maybe confusing to some people. I'll write it out, but then we'll do a few examples, and after doing 1, 2, 3, or 5 examples, you'll get it. For those of you who've seen it already, it'll immediately kind of jog your memory once I start doing like 1 or 2 examples. So let A m by n be a matrix, so this is an m by n matrix. And B, now here's something that's going to be important. N by P. Now I'm naming these things for a particular purpose. Okay? The numbers need to line up in this particular way. Right? So make note of the sizes of these guys. So matrix multiplication, they don't have to be the same size to begin with. So that's another thing that's weird or non-obvious. We define the product AB by, I can take A times B equals C, where, now here I'm going to tell you exactly how to find the matrix C. C is a matrix and its size is actually going to be M by P. Where C M by P is the matrix whose entries are given by, so here's the element in C, Cij. How you obtain Cij, right? The entry in C that is in the ith row and jth column is going to be the ith row of A dot product, the thing I just defined earlier, with the jth column of B. Who's obvious? Not everything is obvious. Okay. So there is a check. Now when you want to add two matrices, the check is easy. They have to be the same size. When it comes to multiplication, the check, it's also easy, but it's a little bit more involved. Is that if the size of A is m by n, colors, I'll use the colors. Maybe a blue. I'm having too much fun with these colors. Okay, so let this be m by n. B, suppose its size is n by p. I can multiply these two things, and the resulting matrix is going to be an m by p. So here's how you can tell that you can multiply two matrices. Okay? When you put them side by side, the inner numbers must be the same to multiply. Okay, when you write down the size of the matrix, if you write it in the order in which you want to multiply them, the inner numbers must match up. If they don't match up, the multiplication is undefined. Now, the outer numbers, the m and the p, this gives you the size of the result. So the inner numbers tell you that yes, multiplication works, I can actually do this process. The outer numbers tells you what size your result should be. Okay, so that's the same thing. Now to actually compute this guy, it's computed by that way. Now, let us actually do, we only have like 15 minutes I think, so we can do a few examples. Oh, and there's something else I want to mention here. Because of this requirement, I don't know what means is the right word to use here, but ultimately what it means or implies matrix multiplication is not commutative. Remember what the word commutative means? It means you can swap the order and nothing will change. So this means if you look at the matrix A times B, it is not the same as the matrix B times A in general. So before, with numbers, you can swap multiplication at will. With matrices, you cannot. It is no longer obvious to swap the order. So it's possible for, it's even possible for one of these to be defined and the other one not even to be defined at all, right? So you can imagine if A is a 3 by 2 and your B is a 2 by 1, then AB, because this is 3 by 2 and that is 2 by 1, these two match up, so bing, that's actually defined. Whereas if I look at BA, this is 2 by 1 and this here is 3 by 2, you would notice that the inner numbers no longer match up. Undefined. that won't work. You can't actually do the process that I described earlier. So there are times when you can get matrices from both and they'll still not be the same thing. There are other times where one is defined while the other isn't. Like, you cannot just swap things around at will anymore. You have to pay attention who's on the left, who's on the right at all times when you're dealing with matrices, because of this particular procedure. So it's not commutative, right? So matrix multiplication is a very non-obvious thing, right? And automatically, because of that, a lot of things like division now become non-obvious. In fact, division doesn't exist. There is no such thing as division in the land of matrices. It doesn't make sense to divide. We'll get to that next time. There's some sort of operation that is in some sense equivalent to division, but it doesn't always work. And it only has the potential of working if you have a square matrix. This is called the inverse of a matrix, which we'll get to. And essentially, this was the problem that I mentioned earlier that my friend told me about. He's like, well, what they wanted was like finding the inverse of this matrix, but it wasn't square, so it was impossible. Let's do some examples here. We'll get through a few of them, and we'll pick up with the rest next time. Whatever I don't do today, try them on your own, and we'll pick up with them tomorrow, or next time we meet, which is Thursday. Okay. So I'm going to give you a bunch so you get used to it. A1 minus 1, Q1, B, 2, 0, minus 1, 1. 1, 2, 3, 0, 2, 4, D, 1, 0, 0, 2, 3, 1. Okay, A. So I want you to compute the following. Compute A. Compute A times B. B. Compute B times A. C. Compute A times D. D. Compute D times A. E. Compute A times C. F. Compute C times A. I'm just swapping the orders a bunch of times so you can see that you'll get different things if you get anything at all. C times D. And D times C. You can get through a few here. Probably the first one is going to be very slow. Maybe get through another one, and then you'll probably try the rest. So let's look at A. We're doing A times B. Now, our A, so this means I'm looking at 1 minus 1, 2, 1. And we never write the dot, just FYI. You just write the two matrices beside each other. You don't put the dot in. Okay, so it's that. Now the first thing you want to do is you want to check that multiplication is actually possible. This guy here is a 2 by 2. That guy here is also a 2 by 2. These guys match up. So it means, bing, we can actually multiply. Now, at the end of this process, the result should be also a 2 by 2. So this is what the result should be. That's the size of the result. Okay? So these two match up, means I can multiply it. The size of the result is also a 2 by 2. If I multiply two 2 by 2 matrices, the result is a 2 by 2 matrix. Okay, so here I'm probably going to kind of write out the result here. So this is the result, like C. Now this is going to be C11, C12, C21, C22, right? I know it's a 2 by 2, so you don't have to write this out initially, but I think it's better to just kind of see where each position goes. Now, what does C11 mean? Well, I'm going to take the first row of A, I'm going to dot product it with the first column of B. Okay, so that thing I did earlier, we're going to do that, and we're going to put that answer in this position. So I'm going to take the first row of A, dot product with the first column of B. So I'm going to take this times this, plus that times that, and that goes here. So that's 1 times 2, plus minus 1 times minus 1. Right? Row times column. Now when I do 2 plus 1, right? That's going to be 3. So that's the first number. I'm going to do it again. So C1, 2, this means take the first row of A, dot product with the second column of B. This, now times that. So I'm going to go horizontally, I'm going to try to flip it vertically and then multiply corresponding components. So it's going to be 1 times 0 plus minus 1 times 1. So here we're going to have 1 times 0 plus minus 1 times 1. Now if I compute that, that's going to be 0 minus 1. That goes here. Then there are no more columns, so the matrix closes. Now I move down to the second row. Now I want you to notice, to get the first row of the result, I use the first row of A. First row times first column, boom. First row times second column, boom. First row times no more columns means close it off, move to the next row, and then repeat the process. Right? So it's very like computation. Right? Which is why a lot of programming is it's done with matrices, because it's very easy to tell a computer how to do this. It's algorithmic. It's a very repetitive process. C21 means take the second row of A, dot product with the first column of B. So we're going to take this times that, 2 times 2 plus 1 times minus 1. And then C22 means take the second row of A, dot with the second column of B. So this is going to be 2 times 0 plus 1 times 1. So now you compute this. This is 4 minus 1. So that's 3. And this is 0 plus 1. That's 1. This is the result of A times B. Notice that the second row of the result came from the second row of A. You also might notice that because of what I mentioned, you're doing a lot of arithmetic all at once. It's very easy to actually mess something up, even though you're doing a simple thing each time. Because you're doing so much of it, it's easy to mess up. So even when I was writing it out, you notice that I wrote things down in a similar order. Right? You might notice that I always put the 2 and the minus 1 in parentheses over here, versus I always put the 0 and the 1 in parentheses over here. Right? I line things up so that there's a kind of symmetry that I can check for. You'll notice that the coefficients are the same across the rows. Right? So I have 1 and minus 1, 1 and minus 1. And the other coefficients are the same across the row at the bottom. So I have a 2 and a 1 and a 2 and a 1. Now in the parentheses, those match up across columns. 2 and minus 1, 2 and minus 1, 0 and 1, 0 and 1. So notice I kind of line things up in such a way that if I have to check my work, or I made a mistake, or I want to make sure that I'm not doing something silly in the beginning, there's a kind of symmetry that you can look for to know that you're putting things in the right position. I would recommend, now even though internally the order that you add things and multiply it doesn't matter, I would pretend that it does, just so that there's a pattern that I'm going with, right? So now if you're multiplying larger things, it'll be easy to get lost, but you kind of have to line them up in a certain way. Okay, so that would be the result. Let's look at B times A quickly. Any questions on this though? Let's quickly do B times A. So this means I do 2, 0, minus 1, 1 times 1 minus 1, 2, 1. Now here, again, we're going to do the same thing. For the 1, 1 position, I need the first row of A, first column of B. First row, first column. First row, second column. First row, first column. Second row, first column. Second row, second column. So it goes like that. Now you just simplify. It's going to be 2 minus 2. That's going to be minus 1 plus 2. That's 1. Plus 1 plus 1. That's 2. And that's the result. I want you to notice that wasn't what we got before. Right? Try the rest for Thursday. Try to make sure you can get through this process relatively quickly without mixing up too much. You can use Wolfram Alpha to check your answers. There's a way to type it there, and we'll pick up with that.